All right, I thought I would do 53b because it's usually considered to be a little bit on the tricky side. With the notation that the stack of four numbers A, B, D, or A, C, D, B, notice I've changed the order here. They're not in the order A, B, C, D, but this is what is given in 53b. A, C, D, B stands for ax to the third plus bx squared plus cx plus d. All right, then I'm meant to look at this differential equation, the derivative of p is equal to x squared. X squared would be denoted in this notation as 0x to the third, so a is 0. 1 x squared, so b, right there, b is 1. 0 x to the first power, so c should be 0, and no constants, so d should be 0. So 0, 0, 0, 1 is the way that x squared is denoted. Okay, then I want to know how the derivative acts on a stack of four numbers with the subscript b prime. Now the idea is b prime is what gives the Rosetta Stone, if you will, the translation between this stack of numbers and a third order polynomial. So what I'm going to do is I'm going to leave d dx as is, and I'm going to write out the polynomial that this stands for. Notice that up here I have a, c, d, b. That means that the order here does not correspond to the order of powers of x, right? The second slot talks about the third to highest power of x, the coefficient on the third to highest power of x. Now down here I've put a, b, c, d because this is going to be easier for me to keep track of in the end. Let's see. The first slot gets attached to x to the third, so indeed I should have an a x to the third. The second slot, where I have a b here, is where c is there. That should be attached to x to the first power. So I will have b x to the first power, right? Because the second slot corresponds to the coefficient of x to the first power. Third slot, right here, third slot, d, corresponds to x to the 0th power, the constant term. So there I need to have a c. And then the last slot corresponds to the coefficient of x to the second power. So this should be plus d x squared. All right. So once again, the idea is these various slots tell you what the coefficient of x to the third, x squared, x, and x to the 0th power are. And you need to follow that convention. It is not that alphabetical order that right. So you do not write these things in alphabetical order. Okay, the order is not alphabetical order here. Now, I can of course calculate this derivative without too much trouble. That is 3 times a x squared plus b plus 0 plus 2d x. Okay. Now, if I'm going to rewrite that in the stack notation here, then the first thing I should put in, the first component, is the coefficient of x to the third. The coefficient of x to the there is no x to the third here. I could put it in by saying plus 0 x to the third. So I look for the coefficient of x to the third, it's 0, and put it in. Next slot, c, is supposed to be the coefficient of x to the first power. I look for the coefficient of x to the first power down here, it's 2d. Then I look for the coefficient, let's see, the coefficient of x to the 0th power, the constant term, it's b. And last, I look for b, the coefficient of x squared, and that's 3a. Okay. So the idea is I have used the b prime notation convention to denote the derivative of this function as the stack of numbers, which the stack of numbers with the b prime subscript on it is a function. It's that function. Okay, So now the idea is to write this differential equation as a matrix equation. Let me figure out what kind of matrix we're going to be dealing with. I want to break this apart into three things. A times some 4 vector plus B times some 4 vector plus C times some 4 vector and plus D times some 4 vector. Now the reason for that is because in the end I'm going to say that is a matrix acting on A, B, C, D, where these vectors make up the columns of the matrix. So let's see. How would I get this stack of numbers? These should all carry B primes, by the way. How would I get this stack of numbers from a sum that looks like this, where only numbers appear inside of these columns? Where does A appear over here? Oh, there's a 3 in the last slot, and there's no A's anywhere else, so 0, 0, 0, 3. So that will give me the 3A right there. There's a B in the second to last slot, so I'll do this. Okay, so now I've got my A's and my B's appearing over there. Let's see, C doesn't appear in here at all, so I should put all zeros in. And then D does appear with a 2 attached to it in the second slot. And so these vectors are the columns of my matrix. 0, 0, 0, 3, 0, 0, 1, 0, 0, 2, 0, 0. Oh, I forgot this guy, didn't I? 0, 0, 0, 0. It's important that they're in that order also. Okay, now notice that all of these guys are carrying B primes. And so B prime really ought to appear over here. What I'm going to do is I'm going to put another parentheses and say after you do this matrix multiplication, apply the interpretation B prime. That means that this with a subscript B prime is a polynomial. Okay, so that is to say, so the differential equations d dx of P is equal to x squared is equivalent to, that's a differential equation, here is an equivalent matrix equation. 0, 0, 0, 3, 0, 0, 1, 0, 0, 0, 0, 0, 0, 2, 0, 0, acting on A, B, C, D, basis B prime. See, that is this matrix that stands for the derivative. So that's the left side of the equation, and A, B, C, D is notation for an arbitrary polynomial of third order. And the right side of the equation, I want to denote x squared with this B prime notation, 0, 0, 0, 1, B prime. And so, if I could figure out how to solve this matrix equation, figure out the numbers A, B, C, D that worked here, then I could use this correspondence right here to figure out which polynomials are solutions to this differential equation. That is, which polynomials really have derivative equal to x squared. Now you can figure that out. You know the antiderivative of x squared. It's 1/3 x to the third plus an arbitrary constant. And we will learn to solve that differential equation not just through the way that you did it in your 21A class, or 21, well, the end of 21A and 21B in the beginning, just through anti-differentiation. We will solve it using a matrix equation. We'll solve the matrix equation and then decode the solutions, A, B, C, D, to get polynomials, which are solutions. Again, our differential equation is equivalent to a matrix equation.